Okay, so the histogram does this and that. We get frequency count on edges. So let's count in Python. Okay, so I've been looking for a mascot for this course. Since we started last year, we had a smiley normal distribution and a sad normal distribution. Just never worked, but it hit me this morning. And that, we're counting things, technically in probability and statistics, and we're doing these histograms. So I think the count is going to be our mascot for this year. If you have better ideas, please let me know. I take these seriously because they spice up the material and just add some levity to an otherwise dry subject, right? So we're going to be counting in Python. So let's count in Python, and this is a very fitting example. Okay, so what I will do with you is get these salaries data. If you go on your canvas, the salaries data is up in one of the modules. Sorry, I have to turn my back to you so I can program together with you, do some hands-on coding. Open up your Jupyter notebooks, please. I hope you already have all that installed. So let me see. Descriptive statistics, graphical. Okay, so we're just gonna count. We're just gonna do the frequency distribution. We're not gonna plot it yet. Okay, we're not going to plot it, but there's data. The salaries data is on your canvas under graphical represent. If you go to modules, there's a module called graphical descriptions of data. It has salaries and miles.txt in it. Yeah. Oh, did I not publish it? Modules, right? Darn it. It should be in modules too. Okay, you can get it from files. Thank you. You can get it from files. Just to log into Canvas now, I have to call just get it from files for now, please, and I'll fix that. I'll add it to the modules. Thank you. Because you have to call the president to log in, and like you have the duo, and then click and wait, and it's like one more thing to do. Okay, let's just create a new notebook. Put the data file next to your Jupyter notebook. Okay, put your data file next to your Jupyter notebook, and let me see. I'm just going to move this to Creston. Hey, guys in the back, can you see? Let me see. Is this better? A little bit better? Okay, so I'm going to do this 2026 in class frequency distribution. Frequency distribution. All right. So the first thing we're going to do is import NumPy as NP, or from NumPy import histogram. But because we're going to use NumPy so much, I might as well just import it as NP, and you should be fairly familiar with that. And next, what I want to do is just simply load up the data file. Now that salaries data, let's call it salaries. Okay, so salaries equal, simply you can load up text data from NumPy. There's a routine called load txt. If the text data is just numbers, one single array, you can just load it up, or two columns or more, it will load up and kind of split it nicely for you. Super powerful, very simple. And then if you just open up that first quotation, if you type salaries, it will autocomplete. So if you press tab, it will autocomplete for you. You know this, I hope. And now we printed we got the salaries. When in doubt, print it out. Print salaries. We see a bunch of values exactly like those values in the slides, but they're not ordered. Okay, and that's fine. They are not in increasing or decreasing order. They're just randomly there. And then from NumPy we do np.histogram. And then if you open parentheses, shift tab, as you know, you can see the function signature, the API, the application programming interface. All of these that have values, these are default values. You don't even have to provide any of this. At a minimum, you need to provide A. What is A? It's an array of input data. The histogram is computed over the flattened array. So you could have a multi-dimensional array. It's just going to make it into one contiguous array of numbers and just do the counts for you. It doesn't care about dimensions and etc. It's just data. It's just going to count all the data. So at a minimum, you need data, but it defaults to 10 bins. That's not often what you want, right? But it just defaults to 10 bins. Okay, so if we do that, salaries, and then it provides two things. So if I were to do result equal np.histogram, and then if you print result contains two things, two items. You see that outer parentheses, and then there's a first array and then the second array. The first array contains the counts, and the second array contains the bin edges, like I said. Now, to rip that apart, often you just want to get both directly, so you do counts, comma, bin edges. That's a common nomenclature. Then you can automatically get counts here and then bin edges here. Okay. Now, let's ask some questions. What is the size? What do you think? So we have 10 bins, right? We have 10 bins. So how many counts? What is the size of this array? It should be 10 because 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Because there are 10 bins. Agreed? And each bin has a count in it. So bin 1 has 2, bin 2 has 1, bin 3 has 0, and so on. What about bin edges? If you notice bin edges, you start at the edge of the first bin and notice it took the minimum, 50,700. Then the edge of the second bin is 53,900, okay, and so on, all the way to the last bin. But then there is, so if you count how many entries, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's 11 entries in bin edges. Why? Because you need that upper limit of that last bin, right? So you need the upper limit of the last bin. So you can think about it as the first bin as being this interval with this interval open, because you need to be at least 1 point less so you don't overlap. Right, so you don't kind of cause trouble where you want to bin things. So this is the first bin, second bin, third bin, fourth, fifth, sixth, seventh bin, eighth bin, ninth bin, and then 10th bin. So always the counts are going to be the same size of the number of bins, the array, but the bin edge is going to be one more. All right. Now we can control the number of bins. We can do bins equals 7. And then it gives me something more similar to what we did earlier on the slides, but it's a little different because here it's automatically starting from 50,700. Okay, it's automatically starting from 50,700. Okay, now what do I want to do next? Okay, let's throw at this a custom bin size. So can we do this? Let's check. If you look at the function signature, you come here and you check and what bins can take. An integer, which is just a single number, so that's what we put here, 7. Or a sequence of scalars or strings. A sequence of scalars, those are numbers. If bins is an integer, it defines the number of equal width bins in the given range, etc. If bins is a sequence, it defines a monotonically increasing array of bin edges, including the rightmost edge, allowing for non-uniform bin width. This is incredibly powerful. So you can tell the histogram, you can tell NumPy to the first bin make it 5,000. The second bin, you could do it 7,500 width. The third bin, you can do it 1,000 width, whatever you like. Or you can make them equally spaced, and you can start from whatever you want. Okay, so that is super powerful to do that. So let's try that. Let's do the bins we did in class in the slides. So if I want to do my bin edges, and it can be just a list, doesn't have to be a NumPy array or anything like that. So you could do 50,000 and then 55,000. No, we can do it more smartly than this, but I'm going to do it the hard way. 60,000, okay, 65,000, and then 70,000, right? And then 75,000. This is horrible. This is, I always say, you could use Python as a calculator, but that's just foolish. This is using Python as a calculator. This needs to be done as like an inline for loop to add all of those together. But we'll elevate to that level soon enough. Okay, 80,000. All right, so we have 1, 2, 3, 4, 5, 6, 7, and then 85,000. That's my last, right? So that's what we had in the slides. Agreed? Did I make a mistake? Yeah, so I had up to 85,000. Okay. Now if I say, my bin edges is going to crash because I didn't execute this. There you go. And then now the counts are identical to what we had in the slides, because we determined the bin edges. And indeed, the bin edges are exactly the bin edges that we provided. Okay, so you give it a sequence, control it however you like. This is super powerful, super flexible, very, very good, very helpful. All in sync? All right.
So would you ever want to do this with variable bin widths?
Possibly. You might want to do it with, but I don't think it will be very informative. It might be, a way to trick the data somehow, or you might have a lot of very small values in some region, but I don't see any reason for why you want to do that, because that technically kind of changes it's like you're changing your x-axis, but you'll have a very wide bin in the middle when you plot the histogram. So we can try this later. I can't think of an example I've faced like that, but that's a good question, Alexa. Thank you. Put your names, please, so I try to remember you. It's a good memory exercise for me. Okay. Relative frequency. So now we did the frequency, or the counts. The relative frequency, it tells you the portion or the proportion of that count relative to the full data. So we counted 3 salaries in the first bin. Is that 10% of all the data? That's all that relative frequency is trying to answer. Okay? And that's helpful because it's easy to think in terms of percentages. Because knowing that, there's 10 people out of 73 people who earn this in this range, okay, that's just a number, but it's easier for us to comprehend it as a percentage. So that's what the relative frequency does. It simply takes the count for a certain bin and divides it by the total number of counts. So you get what? You get a percentage, you get a fraction out of all of your data. So mathematically, you can say this is the count for bin I, for the ith bin. So first bin, what's the count? That's F1 divided by n. N is the total number of observations, okay, or the full count that you have. So, you can do this very easily here. And by just taking this, and okay, I got my bin edges, my total number, my total count is this sum, or just the length of the data, that's 25. And I simply divide 3 by 25, 0 by 25, 6 by 25. So, 3 by 25 is 0.12, and then 0 by 25, 6 by 25, 0.24, and so on and so forth. And so you get this kind of percentage. Okay? Now, to do relative frequency using NumPy's histogram routine, we need to provide something extra. It doesn't automatically do it for you. So we have to provide some extra information to NumPy so that it does the calculation for you. I mean, you can take the counts and then divide them by an array of counts. We should make an array of counts. Anyway, so we take the you can take the counts and divide them by the length of that array, and you get a percentage. All right? Or you can automatically pass that information into the NumPy histogram routine. Both of them will work just fine. All right? But it's a good opportunity to introduce weights to you. We will unlikely be using them moving forward, but it's good to just see this. So there's another option in NumPy's histogram, and it's called weights. Now, to do this, so the weights here is, what's important about weights is that that will be reflected when we calculate weighted means. But what we can do here is we can take, so think of it as each bin can have a different weight. So weights needs to be an array of the same size as your number of bins. And then for each bin, you give it you're going to give it a number. Now here, where all the bins are going to get that same number, and that's going to be 1 over n, or the total number of points, right? Because the way internally Python does it is going to take multiply the weight with the bin size, okay, with the bin count, with the count of the bin. So to achieve what we want to do 3 over 25. So we need to multiply 3 by 1 over 25. And then we need to multiply the other bin 6 by 1 over 25, and so on. So for our case, to achieve the relative frequency, we need an array of weights. Each entry in that array needs to contain the value 1 over n. Okay? Now, we can achieve this very simply by, if we know n, that's the length of our data, or the total number of counts, weights will be an array of ones of size n divided by n. So if you haven't seen this, this will produce, if you haven't seen it, then when in doubt, print it out. So we can do this in Python as well. Actually, I did have this. Okay, so we can do this in Python. Let's count in Python. I'm going to bore you with this for the rest of the semester. Sorry. Someone should make an AI movie about the counting in our statistics course. No, np.ones of size 5, right? It gives you an array of ones of size 5, right? You did that in numerical? Yep. Okay, perfect. So now if we provide, okay, so let me take this and say relative frequency distribution, and then I'll provide weights is equal np.ones. What is the size of my array? It's the length of the salaries, or the size of all my data. The sum of all counts is the total length of the data divided, so let's just say n is equal n salaries, and then we make this of size n and divided by n. And then I'm going to copy paste here. Okay, counts, bin edges, np.histogram, bins, etc. And then you type in weights, and then that's equal weights. Okay. Now, again, you can look at the API or the function signature, and you can see here weights, an array of weights of the same shape as A. Each value only contributes its associated weight towards the bin count instead of 1. Okay. Now, don't confuse this by using the word density. We're not going to touch that right now. Density is not the same as relative frequency. Density has to do with probability densities. When the bin edges shrink to 0, it's a completely different animal to deal with. Okay, so we don't do that right now. So if you do this and then print counts, and then you're going to get these fractions 0.12, 0, 0.24, etc. Now you can also multiply this by 100 so that you get percentages. Okay, I can do my 100. And then you're going to get 12%, 0, 24%, 16%, 40%. But make sure you understand what the numbers mean. Okay? And that's how you get a relative frequency distribution with NumPy histogram. I wish they would just put an option just there. Just give me relative frequency. Okay? We good? Anybody still typing? Speak up or forever hold your breath. Okay. All right. Next is what's called, so the relative frequency is useful because it tells us this many percentage of the sample or the population, whatever you're counting, is in that bin, and so on and so forth. Okay, good. And next is going to be another measure called cumulative frequency. So it feels like we took a detour. What were we doing in the first place? We were looking at graphical descriptions of data, right? And so my goal is to get to plot a histogram, but also on that histogram I want to plot a cumulative distribution, because those are going to translate later into probability density functions and a cumulative distribution function. Okay, so those two concepts are important to start thinking about in this context right now. The cumulative frequency is simply the sum of the frequencies, the counts of a given bin and all the bins previous to it. Okay, so up to a given bin, how many, essentially when you hear, oh, you are in the 50th percentile, you know, or you're in the 75th percentile, there's 75% of the population, you know, below that value that you're at. That's what the cumulative distribution is doing. It's asking the question, what is the total count below that bin that I'm looking at? Okay, and the procedure is pretty simple. You start always from your first bin, so we have 3 in it. In your second bin, the cumulative frequency is the count in the second bin plus whatever is here. So 0 plus 3 is 3. Then you go to this bin. There's 6 in this bin, but then the cumulative count is 6 plus 3. That gives you 9. So now you see in this category, the cumulative count is 9. What this means is that there are 9 members of this array, 9 subjects, 9 people with salaries less than 64,999. Okay, so that's what this is measuring. Saying, okay, how many people are below this bin, and so on and so forth. Okay, this is going to be critical when we do hypothesis testing as well, because we will need these cumulative distributions, because what we will learn later is that you can only compute probability by doing a cumulative distribution on the probability density function. All right, and I hope that will shock you a little bit later, but we'll get to that point. Okay, so you can do cumulative distribution, and you can ask questions like I said, like, okay, you know, the example I have here, among other things, 13 people make $70,000 or less, right? Okay, and you can turn that into a percentage as well if you want, but we're not going to do that. Now, to compute the cumulative frequency in Python, also from NumPy, you import cumulative sum, and you just call it on the counts. So the counts comes from the numpy.histogram, right? There's counts and bin edges, right? So you take that counts. In fact, this routine would do it on any array. It will just add things up on any array. It doesn't have to be the array that you bring from the histogram, but we're going to use it on the array that comes from the histogram because it's what we're after, the cumulative sum. All right, so let's do that in Python. Again, very simple.
If we already import them,
Nope, just numpy.cumulative sum. Okay, so I already have now these counts are on the percentages. Okay, these counts are on the percentages. Now note, so you can do it on the percentages as well, or you can do it on the regular one. So let's start with doing it on the regular one. I'm going to execute everything here to make sure I got everything sorted out. And then cumulative frequency is equal numpy.cumulative sum. And then I'm going to call counts on it. And then print cumulative frequency. And then it does the job for you. So what it did, it took 3. And then in the second entry, 0 plus 3, that's 3. 6 plus 3 is 9. And then 4 plus 9 is 13, and so on, all the way to 25. Now notice the last value is going to be the total count, right? Because all people in the sample make less than $85,000, right? Because that's the sum of the entire population, okay? Or the sample. You can try it on the percentages as well. What should the percentages add up to?
100.
100, yes.
So would doing it on the percentages give you the
Percentage cumulative sum.
percentile?
Yep. Well, it gives you the percentiles based on the bins that you chose. So if the bins you chose might not hit on the 25th percentile, it might end up, let me show you. Okay. So the percentiles, you have to compute them in a different way, and we'll use tools to compute the percentiles. P dot cumulative sum counts. Okay. So you see here, there's 12% of people less, but there's no 25%, right? Because you chose the bins in a way that are not going to hit that 25th or 50th percentile and so on. We'll get to that later. There's another tool to get the quantiles, okay? But that's the interpretation, is that 52% of the people make less than whatever salary. Once we do the plot, it will become easier to see. Okay. Why did you come here, dude? Come down. Get out. Yeah. You know what? Go away. Okay. Get out of the way. All right. So you will also see some slides highlighted in green. Those are extra. There's an extra example that I'm not necessarily going to cover in class. I will still post it for you. And, you know, it gives you an extra work. The chapter has a lot of, like this is example 2.1.6 from the from chapter 2 that was posted in the Canvas. So you can work through that. But when I put it in green means I'm not going to cover it in class, and that you should check it out. Okay, next, finally, we're going to do histogram and relative frequency histograms. This is where we get to plotting. And you know, the definition of the histogram is just simply a type of bar chart that displays the counts of the data that we looked at. But it's not any kind of bar chart. In a bar chart, the bars are not overlapping. They're not continuous. They can be separate. Physics, math, you know, psychology, whatnot, right? Here, the bars are next to each other. They're connected to each other. They represent something entirely different. They look like bars, but it's not a bar chart. As we call it a histogram. And the relative frequency histogram is one where the heights of the bars represent the relative frequency instead of the counts. It's like the same thing. Now, some history, the word, I don't know if you've heard of the guy Pearson. There's Pearson Education. It's like a big education company. He was a physician and he did a lot of good things. But he came up with that word as far as we know. And if you look at the etymology of the word, comes from histos, means anything that stands up, because these are the bars that stand up. And gramma means chart. So chart of things that stand up. I think he meant a bar chart, but you know, they like Latin back in the day or Greek, and so use the word histogram. It's a nice word. Okay, now to plot a histogram in Python, we're going to use matplotlib. And in fact, the routine that we are going to use is also going to give us counts and bin edges. And it looks almost identical to NumPy histogram, but it does a lot more, and it does a graph for us. So from matplotlib, we import matplotlib.pyplot, SPLT, standard stuff we do with Python, plotting, and then we call plt.hist, and we give it, at least we gotta give it data. It defaults to a number of bins. We'll see what that is in Python. But you can also give it bins, similarly to what we did these first two arguments, and even weights. Some of the other arguments are identical to numpy.histogram. Okay, they're the same. They do the same calculation. Okay, so similar to numpy.histogram, this routine also returns the frequency count and the bin edges for you. Okay. Oh, I have multiple animations because I have the count coming. Sorry about that. So okay, so let's go ahead and plot the histogram for these data. So this is what it should look like. So let's try it out. Let's go back to Python over here, and we're going to start with with this guy. Okay. Okay. So let me import first matplotlib. import matplotlib.pyplot as plt. And then we can do simply plt.hist. And what do I need to give it? So we can look at the number of function argument. And obviously, you know, the histogram in matplotlib is much more encompassing, much bigger routine than NumPy histogram. It's trying to do a lot of things. There's all sorts of options to customize the plot. That's up to you to figure out. And GPT can be incredibly helpful here. It's like Googling how can I color the you know, the bins, etc. So ChatGPT or Google will help you a lot, kind of customize things. But the most important argument is the one that doesn't have a value. So all of these are optional arguments. So at a minimum, this needs data, and then it's automatically going to figure out, you know, what it needs to do with the bins. Let's see if it defaults to something here. Bins, okay, is an integer. Let's see. Looks like, okay, so let's see if we don't give it bins. Let's do salaries, what it does. Oh, yeah, it did. It picked its own. It picked its own number of bins. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it defaulted to 10. I think internally it's probably using numpy.histogram. We can verify that. But anyway, this plot we're going to customize it. But just a side note about style and it looks ugly. I'll tell you from now. You need to have some nice bin edges, change the color a little bit, be lighter. But it's also very low resolution. Okay, let me demonstrate that to you. Okay, so I'm gonna zoom in here. Let me see if I can do it smartly. I'm zooming in. And notice, like, it doesn't allow me to zoom in anymore. But notice how clean and clear the fonts are. But look at these guys, right? They all get pixelated, right? They get pixelated. Do you know why that is the case? Did you do that?
We forgot the config inline back.
Okay, good. So that magic. Does anyone else know what Alexa's talking about? Yeah. So this is what type of graph this is. This is called raster graph. A raster graphic is simply a bunch of pixels with colors in them. It doesn't have, it has a finite resolution, which is exactly identical to the number of pixels that are in the figure. But how come that's not the case for the fonts up there? For like 900 and array, those seem to have infinite resolution. If I can continue zooming in, it will look crystal clear, beautiful. The reason is that a font and whatever the text is up there is using what's called vector graphics. And vector graphics, they're not pixels, they're actually formulas that draw curves. The number 3 that you see here and the number 9, there's like a formula that's drawing those points, and every time you zoom in, it redraws it with fresh, clean, almost resolution that is infinite to the eye. So we can achieve this, any plot that you are generating, unlike a picture that you take with your camera, which has a finite resolution. Okay, there's a limit to how much you can zoom in. Then you're going to hit the pixels, and you're going to see all sorts of things. When you draw things in your code, you are drawing them from scratch, so you can draw them as vector graphics. Okay, and vector graphics are the standard, are the way to go. They're the only acceptable graphic that you need to use. So we need to add some, we can do this in Jupyter Notebooks. We just need to add some magic here. And I call this the boilerplate. So all my students in all my other courses, they have the same boilerplate that I use. I have NumPy, I have Matplotlib, I have SciPy, I have a bunch of other things that I import across all of my notebooks. So just that first cell, copy paste it from one notebook to another, and you'll never miss a beat. This is what you need to do. So you add this magic percentage matplotlib inline, and then you have to do this little trick, configure inline backend figure format. Don't ask me why. And then here you're specifying SVG. What does SVG mean? It stands for Scalable Vector Graphics. Okay, that gives you that ability to just redraw things in crystal clear, beautiful resolution. cute little plot. Oh, there she is. We're making a cute little plot. Sorry, Abby, I didn't mean to put you on the spot, but that's gonna stick with us for the semester. So, okay, so once you enable this, then notice the difference here. Oh, look at that. It looks bigger, but that's not the point. Now you can actually, this is being drawn. Look at that. This is being redrawn every time I zoom in, right? It's of the same quality as all of the other text, because these are vector graphics. Now, when you export this to display it in your report, don't export it as PNG or JPEG or GIF. Export it as a scalable vector graphic, aka you can use PDF. Now, the fact that a file is PDF doesn't mean it's scalable vector graphics, but if you want to export a scalable vector graphic, you can export it as a PDF, and it will preserve that. So let me try this with you. Okay. So I can do plt.savefig, and then I'm going to give it my histogram.pdf. That's all you have to do, and then it's going to save it. Okay. Now, let me pull it from my, wow, where is my Finder? I'm going to move this over here. Okay, so I'm going to go to stats. Oh, my desktop is not cluttered with files. It's very clean. So you saw the Finder. All right, so let's see. Where is my file? I'm going to go to lectures, descriptive statistics, et cetera, et cetera. And then, okay, so you can see here, okay, it's my histogram.pdf. And when I double click on it, oh, it didn't show anything. Hold on 1 second. 1 second. I gotta put it here, I think, before it plots. Okay. All right, so now if I open this and put it over here, right? Now that plot is actually, look at that. You can zoom in. It's all clean, beautiful. Okay. Versus if I were to save it as, let me try to save it. I'm going to comment this. And then if you do plt.savefig, my histogram.jpg, and I can specify a DPI, but let's not specify it. Okay, so now I saved it. So let's see. Okay, my histogram.jpg. Okay, so that is going to be raster graphics, not scalable vector graphics. And you can already tell it looks like crap. Look at that, right? Now you can increase the resolution on this by changing the DPI. You can put a DPI of 600 dots per inch, so how many pixels you put within an inch. It will still have a finite resolution. Okay? If your plot is originally vector graphics, keep it vector graphics. It's the best. It's actually less storage, and it does a better job. Okay? All right. So this is our histogram. And zoom in a little bit for those in the back. Now you can beautify this. You worry about that. There's a ton of options. You should try to put edges on these bars, make the color a little transparent. It's like this dark blue just blinds you. I don't know. And then you do the histogram is the distribution of the data. Did we use the bin edges that we wanted to use? We did not. Let me see, because we just used the standard histogram, right? So you can do bins equal 7 if you want. It's going to change it. Or we can do bins equal my bin edges, right? And that should give me the bin edges that I'm interested in. and from 50, 50,000, 55, 5 to 60, all the way to 85. And indeed, I got 3 over 6, and then 4, and then 10, and then 1, and then 1. That gives you the distribution of the data. We call that the distribution of the data. And then you can tell that here there's 3 people in this salary range, 0 people in this range, etc., and so on. Okay? Just kind of becomes self-explanatory. Graphs are indeed worth 1,000 words. Now you can do also the same thing with the relative frequency histogram, and then you can provide the weights the same way we did with numpy.histogram. Okay, 1 over n times 100 if you want, and that becomes a percentage histogram. It's the same thing. And then, like I said, the difference between histogram and a bar chart is that bar chart, the bars do not overlap. They're not adjacent. They're very separate. There's a category, right? Physics, history, math, they are separate categories. Whereas in a histogram, it looks like a bar chart, but it's not. These are bars. They mean something entirely different, and they're overlapping. They're right next to each other. And finally, we'll talk about a few types of graphs. So we're going to be counting a lot. We're going to be plotting a lot of data, and we're going to be plotting much bigger data. And then from the shape of the histogram, you can say things about the data. If all the bars are kind of straight next to each other, then we call that a uniform distribution. If the graph is symmetric, it's symmetric, right? It's kind of split in the middle. It looks mirror image approximately on either side. The one that's interesting is being skewed to the left or skewed to the right. So if it's skewed to the right, when the majority of the data fall to the left side. So there's a lot of data on the left and then little data on the right. So we say that's skewed to the right, and the opposite is true for the left. And then an outlier is a value that falls outside the shape of the distribution. And there's modal. So I'll summarize this. This is much better. So this is called a normal distribution, and it's a symmetric distribution. So this is the bell-shaped curve, right? So it's approximately symmetric, right? But in the continuous limit, it will be 100% symmetric. And the middle line, this is left-skewed distribution because most of the data is to the right. This is a right-skewed distribution because most of the data is to the left. Or what I like to think about this is a right-tailed distribution. So there's a tail, we call this a tail, and typically would have an outlier over here. So something that is way out of the data might be called an outlier. That's how I remember right-skewed and left-skewed as right-tailed and left-tailed. It's just easier for me. This is a uniform distribution, roughly. This is called a bimodal distribution because it has 2 peaks. This is called a trimodal distribution or multimodal distribution. It has multiple peaks. We'll learn about the mode next. So let's take a 5-minute break, and we will continue with some numerical descriptions of data. All right? Let us resume our next order of business, and we'll wrap it up. What's wrong with me today, Scully? Okay. Who remembers Scully from the X-Files? Yeah. So we will resume with this will finish off the discussion on descriptive statistics. That will be it, but it does set the foundation for all the calculations that we will do next. So after graphical descriptions and the histogram, cumulative frequency distribution, we will look at numerical descriptions of data. So that's mean, variance, standard deviation, those sorts of things, mode, etc. All right. My learning objectives, what I hope to convey to you in this chapter. That's chapter 3, by the way, in Warren. It's fairly inspired from that chapter, but it's changing quite a bit. At the end, you'll be able to do the following: define, calculate measures of center. Those are going to be the mean, median, and mode. Identify which one of those is best for a given type of data. Estimate the mean value for a frequency distribution. So if you're not given the full data, if you're only given the bins, can you get the mean? Define and calculate spread and dispersion. So that's variance, standard deviation. We'll talk about the difference between sample and population standard deviations. Define and compute the quartiles and identify outliers in data. And we'll also learn about the box plot. We'll start with measures of center. So here when we're presented with data, What statistics can we run on it? And this literally is the meaning of a statistic on a sample. You're given some sample and you want to get some information about it. The first thing that comes to mind is the average value. That is the simplest statistic you can think about. And it is a measure of center, but it's not the only one because it can mess things up. The mean is not always the best measure of center. There's the median as another measure of center, and there's something called the mode, which is also another measure of center. Center means where does the center of the data lie? If I were to put these on a scale, where would I have to put this on a bar and like drop the data into bins? Where do I have to put, the little thing where the hinge so that the bar is flat and stable? We start with the mean and the average. It's simply an arithmetic mean that's like, okay, what's my average food budget per month? You look at all the money you spent for buying food in the last 6 months or 8 months, and you just sum them all up, divide them by the number of how many times you spent money there. Like you had 1,000 entries because you bought food 1,000 times last week, and then sorry, that's me. Sometimes I'm like running to the grocery store like 7 times. Oh, I feel like I want to have an avocado. You just go get one avocado and come back. But now the kids want an avocado, so they go back because they never eat avocado except for that time where this is a true story. It's the only one time where I was about to enjoy my avocado with honey, but I slice it in the middle, open it, get the seed out, and then put honey on it and just eat it with a spoon. Yes, try it out. Utah honey. Yeah. Okay. Eat it with a spoon. Get it not too ripe, not too hard, just kind of soft enough. All right. I love cooking. I'll give a rant about cooking later. I cook a lot. I really enjoy cooking. It's one of the best therapies you can do. You want to connect to Earth and the planet and etc. Just cook, because you'll appreciate everything that Mother Nature gives us. All right, so back to mathematics. The average is simply the arithmetic mean of the data. We're going to start presenting our data a little bit more formally. Now we're starting to get more serious with our mathematics. Our symbol for a variable, we will call later a random variable, is this capital X, and this could represent a set of data or any one of a data point within your data set. Here I'm representing my data in my sample as the set of observations, x1, x2, radon value on day 1, hour 1, radon value on day 2, hour 2, and so on and so forth. Just a bunch of data. Then the mean of those is simply their sum divided by how many entries there are. Okay? Or in other words, summation of xi over n. When I don't have a subscript and superscript on the summation, what does it mean? It means I'm summing over all possible values. Okay? So in the sample, we have a lowercase n number, so I'm summing up over all of them divided by n. Now, notice the symbol of the sample mean, sample average, is x bar. Okay? That's the symbol of the average of a sample. Now, when somebody's presenting me with data and they show me x bar, I know, oh, that's a sample average, not a population average, because the population average has a different symbol, and it's called mu. Okay? So that's a big distinction. Now start doing statistics, you have to be more rigorous in how you describe the data. Sample mean is going to be different from the population mean. And the population, although we use the same symbol because it's the same variable, this is the population of radon data, it would have probably hundreds more or thousands more data points in it if I were to know them. Okay? I don't necessarily know what's inside the population. But then, if you knew everything about the population, then your population mean symbol is mu, and it's the same formula, arithmetic mean, or all the data, except we run over all the data points, which is given by this capital N. Okay? We will later learn that mu, the population mean, is a property of the population, not really a quantity you calculate, it's a quantity you want to estimate, because true populations are never known. Yeah, I can define this as the population, but that's not really the true population. The population of this class is all the students that are going to come also in the future, so I really don't know the population mean. Okay, but the population mean is generally a property of the population, not something you calculate. We're gonna later estimate the population mean from the sample mean. Okay, so how do we do this in Python? We Pythonify it. Again, NumPy comes to the rescue. And I don't know why I have this mean and median over here. Forget about the median. You're given data, you give the data, you ask NumPy to compute the mean for you, it computes the mean. There's also something called average. It's the same thing. Mean and average mean the same thing. Okay? So let's do our coding activity here with a little bit more serious data. And I want you to download from Canvas. Again, they're not on the module, unfortunately, because I didn't publish the modules, apparently. But they are in the files directory on Canvas. You will see uniform data, right-skewed data, normal data, left-skewed data, bimodal data. Just download all of those data files and put them in a local directory and open a new Jupyter notebook next to it. What are we going to do next? Gonna count. I hope, like my dream, is that by the end of the semester, I'm going to get an from you all. Okay, I know it's like I'm gonna overwhelm you with this. Like one day, that would be like my wish, is that you will all like, let's count. Okay. All right. So let's open up our Jupyter notebooks. Again, I'm gonna turn my back to you. Apologize, but that's the only way I can code and see the screen.
Oh, we are able to access the data.
You are not?
At least in the file.
It is in there. Okay, let me try. Let me do this again.
Unpublished module.
All right. Let me. So even in the files, you can see them under files. You can see them, but you cannot access them. Like, yeah. Did you download it? Oh, okay. Were you?
I guess they are published, but
they are available.
Oh yeah.
I'm getting mixed messages from you guys. Okay, I'm gonna publish the modules. Okay, go in the modules. Should be published now. Okay. It's crazy that when I click publish, like that signal goes through the air to the router, and then either goes to space and goes to the server or Canvas, or just goes some underwater if they have their servers out in Europe, and then updates the server, and then you connect to the server, and that's like a fraction of a second speed of light. That's great. Okay, can you see the files?
There's a bunch of weird symbols in like at least the bimodal data one.
Oh. Were you able to load it? That's yeah, I wouldn't look at it on Canvas. Download it, and let's see if you can load it or not, okay? If you cannot load it, then I'll try to upload them again, okay? I'll try to upload them again. All right. Let me see. Okay. So I'm going to create a new notebook here, and we're going to call it numerical representations of data. We're probably not going to do much. We just barely have a few minutes left. Actually, I'm going to create a new one over here. All right, so let me get that new notebook. Since I wish I never updated to Jupyter Lab. It's horrible. Jupyter Notebook just worked. It did what it needs to do. They didn't do anything new with Jupyter Lab except just mess things up. Now I create a new notebook, and it doesn't like load up automatically in my browser. I have to go back to the directory and double click on the thing, and all right, so in class, what are we going to do here? Numerical descriptions. of data. All right. So what do? We first get our boilerplate out of the way. And again, I'm going to copy this from the previous notebook, import matplotlib, etc. And then I need to import numpy as np. Okay. And then let's start with the first data set, whichever we want. We can do the uniform distribution. Okay. And then so I'm going to call it data mp.load txt uniform data. Okay, if this doesn't work for you, let me know. Did it work for you? It works? Okay, you have a coding error with that. So we'll look at that after class. Okay. So you downloaded it to your local drive, your local folder? Yeah. It has to be next to your Jupyter Notebook. Yeah, unless you provide the path. If you put it somewhere, that's why I tell you to put it right next to your notebook so we don't have to worry about path, because I don't know where you're going to end up putting it. Just move it next to your notebook. Yeah, so this load txt, where is it? It's going to assume it's next to you, next to the Jupyter Notebook. Otherwise, it doesn't know where to look for it, okay? Exactly, right? Or get it from space or something. Okay, so when data is at hand, come on. Plot it to, yes, thank you. Plot it to understand. Okay. All right, so let's plot it. What do? We're going to do a histogram plot because this is just data points. There's no x-axis, right? Doesn't make sense to do a line plot or a scatter plot. I don't know, it's just a count. So let's do a histogram. So we'll do plt.hist, and then just throw data at it, and then, boop. Oh, look at that. It is a uniform distribution. Yep, it is a uniform distribution. That's why the file name is called uniform. Okay, it is a uniform distribution, indeed, and this confirms it. You can change the bins and whatnot, etc. Okay, so where should the mean, when you look at it, where is the center of the data? Is it here or here? Okay, vertical, horizontal. Vertical or horizontal? Okay, vertical. Yeah, so when we look at the mean, what's confusing about histograms, what can trip you is that they look like 2D graphs where the value is on the y-axis. And if I'm looking at any other function and tell you where's the mean, you take the mean on the y-axis, right? Where's the average value of the velocity or the average value of the concentration? You take the average on the y-axis, but not with histograms. Histograms, it's only the counts on the y-axis, but the value of the mean, it's what the variable is, which is on the x-axis. Okay, so whatever this is counting, 0.2 milliliters, 0.4 milliliters, etc., is going to be on the x-axis. So over here, it should probably be close to 0.5. So we can run that, and then you can go np.mean data. Let's see. Yep, 0.496. It's in the limit that I have infinite uniform data. It should be it would be 0.5, but that's the mean value. All right. Godspeed. Have a good weekend. I'll see you next Tuesday.